We're going to discuss deforming contours, what that means, how that relates to contour integration. Let's start with the domain. And our domain will not be simply connected. So I'm going to draw, let's pretend like the blue shaded area is an open area, and it's going to be missing, let's say, this darker blue boundary disk. So let's see how good shading I can get. So we're going to miss that interior guy. And then, it's nice and open, so we don't actually get to the boundary on the outside either. All right, so that is our domain. And let's see, maybe here in purple, we are going to do two contour integrals. So here is one. That's one of our contours. I'm going to call that C1. And I will put an orientation on it at some point. And then here is going to be C2. So that's another one, C2. And suppose that we have, so here we have our domain D. So we're going to suppose F is analytic on D. And C1 and C2 are two contours that can be deformed into each other. So what does that mean? Well, imagine for a moment that you put a balloon inside of C1. So you have a balloon in the middle of C1 and you inflate it with air. If you inflate it with air, what's going to happen? Well, the edges, C1 itself is going to be pushed into C2, and it's going to be pushed into C2 in such a way that you're not going to go over any gaps up to my shading. You're not going to go over any gaps in D. So these contours can be deformed into each other, and you can imagine just grabbing C1 with your hands and stretching it out, or not necessarily conversely, but if you interchange the roles of C1 and C2, you can imagine grabbing C2 with your hands and kind of stretching it in on all sides, or pushing it in on all sides. Okay? So these contours can be deformed into one another. And so the question is, does the integral over C1 of f have anything to do with the integral over C2 of f? So let me just put a question mark in between them. And so what we're going to do is we are going to make a new contour. So I'm going to add in this kind of red piece, and I'm going to mark points A and B where the red pieces intersect the two contours C1 and C2. And on the outer contour, we're going to go around in the usual way. So imagine starting at A and then going around that contour in a way such that the interior of the region's on our left. And then when we hit A, we're going to not finish our contour, but we're going to go inside. And we're going to go the wrong way around C1. And then we are going to go back to A, and that will finish our closed contour. Now, if we look at the area between the curves, that the curves care about, there's no holes in that area. So this path where we go around C2, go down to A, go around B, go up, if we just look on our left as we walk, that region that's bounded has no holes. So what this is telling us then is that this path where we go around C1, then we go from A to B, then we go from B to A, and then we go around, then we go around C2, but we go around C2 in the wrong direction. and then we go back from B to A, that is the that's a contour integral around a simple closed contour where the region that's bounded is simply connected. So what this tells us is this integral is zero by the Cauchy-Gorsat theorem. But the integral from b to a is just the negative of the integral from a to b. So these pieces actually cancel with each other. And what we get is the integral over c1 of f is equal to the integral over c2 of f. And this is called deformation of contours, or the principle of deformation of contours, however you want to say it.